Hey, good morning, everybody. This is Mr. Ainsworth again, and we're going to get into lesson 8.2 in AP Pre-Calc here, and we're going to be talking about complex numbers and how to graph them, how to work with them, how to change them to polar form and trig form, and get used to some new concepts here. So here we go. So back in time, here in elementary school, you learned how to graph real numbers on a real number line. And later on, when you got a little bit older here, you also learned that there was a new set of numbers called complex numbers that involved the real and the imaginary numbers put together in through addition or subtraction. So let's get right into it. Part one here deals with just the basics here. This is the part that you know from the previous course probably. And it's just remind you how to graph complex numbers on the complex plane, also known as the Argand diagram. Argand was a mathematician long ago who actually came up with the idea of getting a real and imaginary axis so you can actually visualize how to graph a complex number. And then from that, mathematicians developed many different things, as we're going to get into today. So number one, consider the complex number 2 plus 3i. What is the real component, and what is the imaginary component, and what is the general Cartesian form in general? Okay, when I say Cartesian form here, I'm talking about rectangular form. So those are the same thing. So Cartesian form is Cartesian form. Let's talk about that. That's a plus bi, where a is your real part. Okay, so let's see here. A is the real part. Okay, and b, all right, b is your imaginary, bi is your imaginary part or component. So b, the coefficient of I there is your is equal to your imaginary component part. All right, so when you compare 3 plus 2i, so 3 plus 2i here, to a plus bi, you'll notice that a equals 3. All right, that's the real part. Hopefully that's pretty obvious right there. And then b is not 2i. b is 2, the coefficient of I, and that's your imaginary part. Okay, so just keep that in mind. All right, so we have imaginary plus a real, you get a complex number. All right, now when you graph them as ordered pairs, as so. So when you take 2 plus 3i here, you interpret it as a comma b when you graph. Okay, so a plus bi here. So you're going to interpret 2 plus 3i as 2 comma 3. So basically it's a comma b. Okay, and when you do that, you're going to go 2 units right on the real axis. All right, and then 3 units up on the imaginary axis. So notice I labeled the axes already. On the real axis, it's the horizontal. And then, of course, you got the imaginary axis on the vertical. So to get to 2 comma 3 and plot your first complex number, which we call z1 in general, all right, we're going to go 2 right and 3 up. So 2 right, 3 up, and there's your first complex number. Okay, that'd be 2 plus 3i. Again, you simply go 2 to the right and 3 up, and then you graph the complex number, which we call z1 right there. z2, our second complex number, all right, can be interpreted as -4 comma -5 as an ordered pair, which means you got to go left 4, down 5. And if you go left 4, right, and down 5, that's approximately right here, and there's z2, all right, -4 comma -5 as an ordered pair. Okay, so you just take a look at the components of the complex number, you write them as an ordered pair, and you plot them as normal. Okay, it's actually not that difficult. So just be careful here. The real part is root 3, and imaginary part b is 1. So this is going to be root 3, comma 1. And root 3, as you guys know with me, is about 1.7. So 1.7 comma 1. So you just approximate this one. So you go 1.7 to the right, and then up 1. So right about there approximately, and that's z3. All right, z4, 2 to the right. Now 2 times 1.7, so 2 times 1.7, that's about 3.4. So you're going to have to approximate this as 2 comma 3.4 in terms of a decimal. So it's right 2 up 3.5 almost. So right about, ooh, that's close enough. That's z4. All right, 2 to the right and 3.4, almost 3.5 up. All right, how about these other numbers? Check this out. How do you graph these? Well, you got to kick in your previous knowledge, right? So you got to know what 60 degrees and sine of 60 degrees is. Well, we know our 30, 60, 90, don't we? Yes, we do. Okay, so I'm going to draw one. Or you can use your unit circle, of course. And we know that sine of 6, or so, let me see. So let's get our trig going here. Oh, yeah. So katoa. There we go. Or, like I said, you can use your unit circle, right? So you got cosine of 60 degrees is 1/2. So we have z5 is equal to 2 times 1/2. So you want to evaluate these things. Sine of 60 degrees is root 3 over 2. So we're going to have I times, let's start over here. I times root 3 divided by 2. All right, distribute through the 2. 2 times 1/2 is 1. And then 2 times I root 3 is 2I root 3. Divide that by 2. You got to simplify a little bit. You get 1 plus, all right, I root 3. And then as you interpret that, you go 1 comma root 3, which, as I talked about earlier, is about 1 comma 1.7. And that is Z5. All right, so we're going to go 1 to the right and 1.17 up. So about right about here or so, and there is Z5. 1 to the right and almost 2 up. And that's how the game is played. And the other one here is Z6, our last one here. Well, let me see. The reference angle for 7 pi fourths is pi fourths, so we should probably draw the 45, 45, 90. Switch triangles here. Okay, so the sides are 1 and 1, and we know that the cosine of 45 degrees, or pi fourths, is rad 2 over 2. This is quadrant 4, and cosine is positive there. So this is going to be equal to root 2 times rad 2 over 2 plus I times, the sign's negative down there, so I'm going to write down a negative rad 2 over 2. Okay, distribute through. Okay, so here we go. So root 2 times root 2 over 2 plus root 2 times I. Actually, there's a minus in there, so I'm going to just make it a minus sign, but make it easier. So minus, okay, root 2 times I root 2 over 2. Okay, so you got to simplify a little bit here. Rad 2 over 2 is, well, it's 2. Divided by 2 is 1. Okay, so we have 1 there. So 1 minus 1i. Okay, again, root 2 times root 2 is 2. Divided by 2 is 1. So you get 1 minus I. So my sixth complex number is 1 comma negative 1. As an ordered pair, that puts you in quadrant 4. So I got to go right one, down one. And there's Z6. Okay. So again, we're just applying the trig that we already know from previous lessons and our knowledge of the special right triangles or the unit circle, either one, to graph a complex number as an ordered pair. All right, that's skill number 1, graphing a complex number on the complex plane. All right, part 2. Now, how far is the complex number from the pole or the origin? Well, we call that the modulus, or the magnitude of the complex number. So how do we do that? So let's go ahead and just do a little diagram here. All right, so let's say that our complex number is a plus bi. So what I'm going to do is I'm going to go a units to the right. Okay, I'm going to go b units up. All right, this is in general now, so a comma b. And you're here. There's your complex number, z equals a plus bi. You've seen this drawing before. Nothing new. I did this when we did polar. And the distance between the point and the pole, this is the pole, is called the radius in polar form, right? So we call that r in polar form. But it's also called the modulus. And the modulus has a special look right here. It's the absolute value of z. So the absolute value of z, where z is your complex number. Okay, so if I ask you to find the absolute value of z, I'm talking about the modulus here, and that's the absolute value of a plus bi. The question is, how do you do that? So that's what I want to get into. So you have this right triangle here, and of course, whenever you have a right triangle, the Pythagorean theorem kicks in. All right, and that's exactly what we want to do, is we want to kick in the Pythagorean theorem, which you guys all know extremely well. Okay, so there's nothing new. We're going to take a squared plus b squared. So leg squared plus leg squared is equal to the radius squared. And again, the distance between the point and the pole is called the modulus. So r here is the same thing as the absolute value of z. So I got to solve for r here in this case, which gives me the modulus. Okay, it's the same thing. So whether I say the radius in polar form or the modulus, which is just the distance between the pole and the number, right? Kick in your Pythagorean theorem every time. Of course, you got a square root, right? Square root both sides. And what does that give you? Well, the square root of r squared is r, and that's equal to the square root of a squared plus b squared here. And again, the absolute value of z is just a symbol, okay? It's a symbol representing the modulus, or the distance between the complex number and the pole. That's it. It's actually maybe abstract in the beginning, but it's actually very, very simple. Okay, could we call this the modulus? That's singular. Or if you want to talk about more than one, that's moduli, kind of like octopus and octopi, right? Or cactus and cacti, same thing. But all this is just the distance, okay, from, all right, the point, the complex number, all right, to the pole. And when I say the pole, I'm talking about the origin. Okay, there we go. It's actually very, very simple. Okay, take the square root of a squared plus b squared, and that's it. And you guys are going to get so good at this, you can probably do a lot of it in your head. Okay, so the general form of any complex number is always a plus bi in general. Okay, so a is 5 here and b is 12. So when I figure out the modulus here, I'm going to take the absolute value of z1, and that means I got to take the square root of 5 squared plus 12 squared. Well, what does that give us? Well, let me see. Square of 5 is 25. 12 squared is 144. Yeah, the two, you get this, you get 169, but yeah, square root, right? And believe it or not, that's a perfect square, and that's 13. Okay, so the absolute value of the first complex number is 13, and we call that the modulus, okay? The distance from the point to the pole. And if you graph that, you'd have a right triangle with sides 5, 12, and 13. So just draw a little picture here, just for funsies right now. Okay, watch this. Okay, so 5, here goes 5, and then up. Whoa. Okay, up 12. So 5 here, 12 here. All right, the distance here would be 13. 5, 12, 13. It's actually one of those very famous set of triples called a Pythagorean triple. Okay, you see it. You saw 3, 4, 5 before. That's the smallest one. And now you saw another one, 5, 12, 13. All right, how about this one? Okay, so pause the video now and go ahead and you try it. And then when you're ready, press play and then check your work. All right, let's check your work. So the absolute value of z2 is going to be the square root of 6 squared plus 8 squared. And again, you square a and b, not the I. Okay, remember only the coefficients, the real and imaginary components. All right, so the square root of, let me see, 6 squared is 36, 8 squared is 64. You add the two, you get the square root of 100, which everybody knows is 10. All right, so we have another triple here. All right, it's called the 6, 8, 10 triple. All right, one more here. Let's see what we got here. So the absolute value of our third complex number is z3. We take the absolute value of 8 squared plus 15 squared. And that gives us a square root of 64 plus 225. Add the two, you get the square root of 289. And believe it or not, that's a perfect square, and you get 17. So we have another triple, okay? 8, 15, 17 is another Pythagorean triple. So I just gave you guys 3 of them, okay? Obviously, that was purposely designed. All right, know your Pythagorean triples. Okay, that's it. That's how you find the modulus, or the magnitude of the complex number. It's the distance from the point, which I'm talking about the complex number here, to the origin of the pole. Pretty straightforward. All right, now something a little bit more in depth. We're going to convert your Cartesian form of a complex number, which is a plus bi. All right, we also call that rectangular form too, depending on, how you were taught. It's called either rectangular form or Cartesian form. of a complex number to polar form, which you guys already know is r comma theta, okay, where r is the radius, and then theta is your polar angle. Okay, so I talked about in the previous lesson right through here. And our new form, trig form here, involves sine and cosine. So z, the general complex number, is r times cosine theta plus I sine theta. So where does this come from? Where does this new trig form come from? And so what I want to do is start with that, and I want to derive it first before we actually apply it. All right, so let's get right into it. So here we go. Let's draw the same picture again. Believe it or not, it's the same picture. So when you graph a comma b, remember a plus bi is interpreted on the graph as an ordered pair a comma b. So I'm going to go a units to the right. I'm going to go b units up. So a here, b here. And then I've got my radius here, r. And the theta right here. Theta is the polar angle here between the real axis and the modulus, or the radius. And our point here, z, is right here. And that's our complex number a plus bi. All right, so having this little picture here, believe it or not, you can derive everything you want. It's actually pretty simple, and a lot of it you already know. So Kato, let's go over the definitions here first. So we know that cosine of theta is the adjacent side, all right, divided by the hypotenuse, as you guys already know. So in this case, it's a divided by r. Sine theta is the opposite side of the angle, which is b divided by r. And you guys probably have other definitions in terms of x and y. It's the same thing, guys. Instead of x to r, I have a to r. Instead of y to r for sine, I have b to r. It's just the vertical divided by the hypotenuse, so nothing new here, guys. And you guys already know that tan theta is usually y to x, all right? But it's also, in this case, we're using b and a here because we're dealing with a complex number. It's b divided by a. And believe it or not, if you know these three definitions here, you can derive the famous trig form of a complex number, which is this r times cosine theta plus I sine theta. All right, so how do we do this? Well, what you want to do is you want to solve for a and b in this diagram, or in these ratios. Okay, so let's do that. So in the first one here, I simply multiply both sides by r, and what do I get? Well, I get a is equal to r times cosine of theta. On my next one here, I want to do the same thing. So I multiply both sides by r, and I get b is equal to r times the sine of theta. I've done this before with polar form, you guys. And then I'm not going to worry about tangent of theta right now. This right here is used to find the polar angle. Okay, so now what I want to do is I want to start off with my general Cartesian form. So I know that a is a plus bi in general. Well, guess what? I know a is r cosine theta, so I want to substitute this in. So r times the cosine of theta, right, plus bi. So b is r sine theta, so r times sine theta, all right, times I. That's a times. Okay, so now what I want to do is I want to kind of factor out a common factor here, and you'll notice that r is in common, and whenever a factor is in common, you factor it out. So factor out the r here, the radius, okay, which is called r. Let's do that. So I'm going to start off with that. So now my final result becomes r times cosine theta plus, I'm going to bring the I in front because I'm not multiplying the polar angle by I. So just to make sure no one's confused on that, bring it in front and write it as I times sine theta. And there you go. And this is called trig form, okay, or trigonometric form. So it is the way to go from Cartesian form of a complex number to trig form involving sine and cosine. And then, of course, polar form is just r comma theta. All right, so it's one thing going over that as definitions, right? So let's apply it here and see what happens. All right, so I'm starting off with a very simple example here, 2 plus 2i, all right? Our complex number is 2 plus 2i in quadrant 1. And what we want to do is find the modulus, the polar angle, and write it in trig form. All right, so let's do it. Okay, so the first thing we do is let's go ahead and sketch it just to graph it, just to see what's going on, right? So two right, two up. So graphing is pretty straightforward. Here's your theta, there's your polar angle. So it's 2 comma 2. So there's z, 2 plus 2I, and radius is here. Or the absolute value of z, right? That's called the modulus. All right, so let's find the modulus first. So r is equal to, again, it's the absolute value of z. If you call this z, z is equal to 2 plus 2I. Okay, and that's equal to the square root of a squared plus b squared. And a is 2 and b is 2, because remember it's a plus bi, so they're both 2. So the square root of 2 squared plus 2 squared, that's the square root of 4 plus 4, or the square root of 8. And before we use that in our trig form, let's simplify it here. So the square root of 8 is the square root of 4 times the square root of 2, so the radius is actually 2 rad 2. Okay, so from here to here, I just simplify the root. Just simplify, right? And that right there is your modulus. Okay, now the polar angle. How do we do that? Well, the polar angle, believe it or not, you can use any one of these three trig functions. However, most people use this one right here, all right, the tangent function to find, all right, the polar angle theta. I use this every time. Just turns out to be easier, that's all. So I'm going to write that down. So tan theta in general is whatever b divided by a is, right? And you guys know that when you solve for theta, you got to use the inverse. So the very first thing we do is we substitute a and b in. So I know that tan theta here is equal to 2 divided by 2, or 1. Now we know this is in quadrant 1, and when we take the inverse tangent, okay, of 1, we're looking for either a quadrant 1 or 4 answer, and because this is positive, this has to be quadrant 1. Okay, so theta must be in quadrant 1. That makes sense because we graphed it and it's in quadrant 1. But remember, the inverse function is restricted from negative pi halves to pi halves. So it has to be either quadrant 1 or 4. But like I said, this is positive and it has to be a quadrant 1 angle. And as you guys already know, there's only one angle that you know of that has a tangent ratio of 1. And guess what? That's 45 degrees, or pi fourths. Opposite divided by adjacent, which is 1. So we know the tangent of pi fourths is 1, so theta is pi fourths. Radians, 45 degrees, but we're in radians right now, so let's just stay in radians. You can say 45 degrees if you want, but let's keep it in radians here. So trig form now, here we go. We're going to substitute this in. We got 2 rad 2. Again, you start off with the radius. In fact, you know what? Let me write it down up here. Let me put it in red and then do my substitution. Okay. So in general, it's always r times cosine theta plus I sine theta. This is your general trig form up here at the top of the screen. That's it. Okay, that's the general form. All right, so now all you do is just substitute your numbers in. So our complex number in trig form looks like 2 rad 2, which is your modulus, times cosine of pi fourths plus I sine pi fourths, if you want to express your answer in radians. And that's it. There we go. That's trig form. Polar form, if you want general polar form, that would be easy too. So let me see. I'll throw this in here, just even though it's not asked. Let's do it anyways. Okay, so polar form is r comma theta, as you guys know. And so it would just be 2 rad 2 comma pi fourths. There we go. There's polar form. So now you have all three forms. You have Cartesian form, which is right here. This is Cartesian form, or some people call this rectangular form, the given complex number that you're used to seeing. And then you got trig form and you got polar form, all three forms. Pretty cool. I bet you guys didn't know before today that you could write complex numbers in multiple ways. Haha, yes you can. All right, one more example here, and then I'm going to pause and then we'll do the rest in my next part of the video here. So pause the video, give this one a shot, and then when you're ready, go ahead and press play and check your work. All right, I'm going to assume that you did that. So let's check your work here. I'm going to graph just so you can see it here. So Here you go 3 root 3 to the right, and then you go up 3. And there's a little sketch of your number there. So we'll call this one Z2, I guess. So there's Z2, which is 3 plus 3. Excuse me, I didn't write that correctly. 3 root 3 plus 3i. There we go. All right, now to find the modulus. Okay, so here we go. The modulus is here. We can call it z, or we can call it the radius. Either one, it's the same thing. The absolute value of z is just a symbol for the modulus or the radius. So let's take the absolute value of 3 root 3 plus 3i. Again, this is a and this is b. So let's substitute them in. So you got to take the 3 root 3 and square it, plus 3 squared. And again, you're only squaring the a and b, not the I. Keep that in mind. And then here at this point, when you take 3 root 3 and square it, you square both. So 3 squared is 9. Root 3 squared is just 3. 9 times 3 is 27. Okay, so there we go. We got 27 there. So 27 plus 9, guess what? That's 36. And if you take the square root of 36, you get 6. All right, so the radius, or you can say the absolute value of z, which is your modulus, is 6. Cool, but you didn't realize that it was going to end up being kind of nice. Okay, so now the polar angle. We're talking about theta now. And again, you always use tan theta equals b divided by a. So I'm going to write that down again. Always write down your definitions right there here. And so tan theta is going to be equal to b, which is 3, divided by 3 rad 3, which is just 1 divided by rad 3. And this ratio here exists on the 30, 60, 90. You should recognize this. Okay, so right there, we know on this triangle here that the tangent of 30 degrees, or pi 6, is equal to 1 over root 3. So you really have to know your ratios really well, and you have to be able to recognize them. That number there, 1 over rad 3, has been seen a lot, okay, or root 3 over 3 if you rationalize it. Same thing. So now I know it's quadrant 1 because it's positive, so theta is in quadrant 1. Also, I graphed it, so I also know it's quadrant 1. And when you take the inverse tangent of 1 divided by rad 3, you're looking for an angle whose tangent ratio is 1 over root 3, which happens to be pi 6. So theta here is pi 6 radians, 30 degrees in degrees, if you want to express your answer in degrees, right? And then trig form, here we go. R, which is 6, times cosine theta, which is pi 6, plus I times the sine of theta, which is pi 6. And that right there is called trig form. And again, this skill right here is just takes getting used to, but it's pretty straightforward out, obviously. And then if you also want to write it in polar form, if you wanted to just throw that in there, remember polar form is r comma theta. We know both of them, so it's just 6 comma pi 6. Every complex number can be written 3 different ways. We've got Cartesian form, that was given, okay, which is also called rectangular form. Okay, we're given that. That's form number 1. Form number 2, trig form maybe, right? And then form 3 is polar form, r comma theta. And you just got to get practice. You got to get good, all right? And that's why you got to do your practice here. So finish examples 3 and 4, do your check for understanding, and start your homework, okay? Because perfect practice leads to better understanding. Again, so always check your work with mine. Go into Canvas and check it with the instructor's notes, and make sure you guys are doing a good job, all right? And I hope to see you in class. Take care. This is Mr. Aynesworth. Bye-bye.